So in the previous lecture we had used the following two exercises. So one, let's show that the real line is homeomorphic to the interval 0, 1. So let's see how to do this. I just want to sketch a quick proof. So we will give a homeomorphism from the real line to -1, 1, and you can easily check that using a linear isomorphism that the interval -1, 1 is homeomorphic to 0, 1, to the interval 0, 1. Okay, so let's give a map from R to -1, 1. So we simply send x to x divided by mod x plus 1. Okay, and easy to check. This is bijective and continuous, right? And the inverse of this map is given by -1, 1 to R, y maps to y upon 1 minus mod y. Yeah, and this is also continuous. So so to check that these are bijective and continuous, both these maps, that's left as an exercise. This is one exercise. The other exercise I had mentioned was, so we take, let x and y be topological spaces. Fix a point small x in x and consider the inclusion from y to x cross y given by y maps to x comma y. Okay, so clearly this factor is like this. So I, and let's call this f naught, let's call this map f. Yeah, so then f naught is a homeomorphism. Yeah, obviously x cross y has the subspace topology. From x cross y. So let's quickly check this. So f is continuous. Okay, as both the projections are continuous. So recall we had seen that to give a map to a product, it's enough to give a continuous map to a product, it's enough to give continuous maps to each of the factors, and both the factors, the first factor is just the constant map y to x, that is obviously continuous, and the second factor is the identity. So both these are continuous, and since the image lands in x naught, in x cross y, it follows that f naught is continuous, right? Here we are using the following exercise. So let's say, not exercise, result which we had proved when we talked about the subspace topology. Suppose A to B we have continuous map f, and let's say the image lands inside a subset C of B, and then this f factors as f naught. So if we give C the subspace topology, then this map f naught from A to C is continuous. Okay, so f naught is bijective is clear. Is clear. So therefore, to show that f naught is a homeomorphism, is a homeomorphism. It is enough to show that f naught of V is open for an open V in Y, right? But f naught of V is exactly equal to x cross V, and this is equal to x cross V, this open set intersected with x cross Y, this subspace, right? Thus, f naught of V is open, which implies f naught is a homeomorphism. Okay, so this completes both the exercises which were mentioned in the previous lecture. So now let's proceed with our discussion on compactness. So last time we proved that a closed subspace of a compact space is compact. Okay. So this time let us begin today's lecture with the following proposition. Let X be a topological space and let Y contained in X be a subspace which is compact. Right. So here Y is a subspace of X, and therefore it inherits the subspace topology, and this topological space is compact. That is our assumption with the subspace topology. So then our claim is then Y is closed in X. Okay, so let us prove this. So we shall show that the set X minus Y is open in X. Okay, so once again let's make a picture. Let's say this is our X and say this is our Y. So let's pick up any point X over here. So let X be in X minus Y. It's a point outside Y. So we need to show that there's a small neighborhood of, there's a small open set around X which does not meet Y. Right. So we choose any Y in Y. Right. So let's say this is Y. Then as X is housed off, so as I had mentioned, it is from now on we will always be assuming that our topological spaces are housed off if not mentioned. But okay, as X is housed off, there exist open sets UY containing X and VY containing Y. So this is our UY and this is our VY, such that UY intersection VY is empty. Right. So we can do this. So we can do this for all Y in Y. Right. So then the sets V sub Y form an open cover for Y. So that is, we can write Y as, so Y is contained, so Y is contained in this union Y in Y, V sub Y. Yeah. So this implies that Y is equal to union Y in Y, y intersection v sub y, and since this is an open cover, this has a finite subcover, so this is equal to union I equal to 1 to n y intersection v sub yi. Right? So this implies that y is actually contained in the union of finitely many of these v sub yi. Okay. So now let u be equal to the intersection I equal to 1 to n u sub yi. Now each of these u sub y's is contained x, so therefore this implies that, and there is a finite intersection, so this implies that u is an open subset of x and x is in u. Okay. So we claim that. So let's look at u intersected with the union of yi's I equal to 1 to n v yi's. This is contained in the union I equal to 1 to n u intersected v sub yi's, which is contained in the union I equal to 1 to n. U is contained in u sub yi intersected v sub yi, but each of these is empty, so this is equal to empty. Right. So this implies that u intersected this union is empty. This implies that u intersected y, which is contained in u intersected this union v sub yi, as we saw that y is contained in this union, is equal to empty. Right. So thus, given this point x in x minus y, we have found an open set u contained in x, open in x, such that x belongs to u and u is contained in x minus y. Thus x minus y is open. So this completes the proof of the proposition. Okay. So as a result of this proposition, using this proposition, we will prove this very useful theorem. Let y contained in Rn be a subspace, then y is compact if and only if y is closed and bounded. So I haven't defined what bounded means, but it means the obvious. So let y contained in Rn be a subspace. We say that y is bounded if there exists some m positive such that y is contained in the ball of radius m around the origin. Let's say in the Euclidean metric. Okay, so let's prove this theorem. So let us first assume that y is compact, right? So we can write y. So then y. So first note that Rn we can write as the union n greater than or equal to 1 open balls of radius n. So this is an open cover for Rn because every point is contained in one of these balls, open balls, right? These keep getting larger and larger, right? So this implies that y is equal to, we simply intersect both sides with y intersected b01, b0n. This is an open cover for y, right? And since y is compact, this has a finite subcover. Right? But these balls are contained, so B01 is contained in B02, is contained in B03, and so on. So this implies that there exists some n such that y is contained in B01. Thus y is bounded. Right? Because of this previous proposition says that Rn is a Hausdorff topological space and we have y which is compact, so y is also closed. Right? So the previous proposition implies that y is closed. Yeah. So thus y is closed and bounded. Okay. So this proves one direction. So conversely, assume that y is closed and bounded. Right. So since y is bounded, we can find a M large very large such that y is contained in this product of these intervals, right? So y is bounded means y is contained in some large open ball, and this open ball we can put inside a square like this, inside a closed square. Okay, so or y is this thing. Okay, so moreover, so note that so we proved that 0, 1 is compact as 0, 1 is homeomorphic to, we can just in fact even write a linear homeomorphism. This implies minus m comma m is compact. This implies minus m comma m to the n is compact. Right. So as y is closed in Rn, this implies y is also closed in this subset, right? And by what we proved in the previous lecture, we proved that closed subspace of a compact space is compact. Yeah. So using that, right? So as closed subspace of a compact space is compact, this implies y is compact. Right. So this completes the proof of the theorem. Okay. So as an application of this theorem, let us prove that SON is compact. So recall, so as an application, right? So recall SON, or the same proof for ON will work. SON is the set of those matrices A with real entries such that A transpose A is equal to identity, n cross n identity. Yeah. So claim SON, this has the subspace topology from MNR, right? And MNR we can identify with Rn square, right? So is compact. So our claim is that SON is compact. Yeah. So it suffices to show that SON is closed and bounded. Okay. So let's look at this map. So let's first show that SON is closed. So let us consider the map from MNR to MNR cross R. So this map is given by A gets mapped to A transpose A, comma, determinant of A. Oh, sorry, I forgot to put the determinant condition. Okay, so we claim that this map is continuous. Right. So to show that it is continuous, it's enough to show that first we look at the map from MNR to MNR. A goes to A transpose A. This map is continuous, and the map from MNR to R, A goes to determinant of A. So this map is continuous is clear because the determinant of A is a polynomial in the entries of A, and we know that polynomial, the entries of A are simply the projection maps, and projection maps are continuous from this product, and polynomials, therefore polynomials in these continuous maps are continuous. Let's look at this map over here. So once again, MNR is identified with Rn square with the product topology, right? So to say that this map is continuous, it's enough to say that each of the coordinate functions is continuous. But once again, when we look at A transpose A, the coordinate functions are polynomials in the entries of A. Yeah. So thus A goes to A transpose A is continuous, right? So this shows that phi is continuous, right? So now the point identity n cross n comma 1 in MNR cross R is a closed subspace, is a closed subset. In fact, in any Rm, a point, so we can just take any point, a point A1, A2 up to Am is this, just the single set is a closed subspace. Okay, so this implies that phi inverse of this identity n cross n comma 1 is a closed subspace. but this is precisely SON. Okay. So therefore SON is closed, and next let's see that SON is bounded. So this is easy, because when we look at the condition A transpose A is equal to identity, so if A is the matrix A11, A12 and so on, A21, right. So then A transpose A is equal to identity, so this will imply that right. So when we look at the ith entry of A transpose A, this is equal to summation j equal to 1 to n AJI square. Okay, and since this A transpose A is identity, this sum has to be equal to 1, right. And when we take sum over all i's, this implies summation I comma j Aij square is equal to n, right, for every A in SON, right. So thus SON is bounded, right. I mean, the topology on Rn square is given by this Euclidean metric, and what we have just proved is that every element A is contained in the ball around 0 of radius square root n. Okay, I can add a square root n plus 1. Okay. Okay, so we will end this lecture here.